So problems, okay. Um, so uh, today we will uh, go through quick introduction to PyTorch framework. Uh, so the main data type in Torch is called tensor. Like main data type in NumPy array was NP array. The main data type in PyTorch is tensor. So for example, we can create a variable of 5 and to make this torch variable, we cast to torch tensor, and torch has different data types like int, 8 int, long int, 64-bit, floats 16, 32. So you can indicate data type as well when you create the variable. Also, you can create vector of ones or zeros, so very similar to NumPy. Here I create the vector of ones of size 6, and default data type is float 32. So how many significant digits are in float 32? Oh, by the way, Ryan, you didn't submit the midterm. Oh. Do you want to do that? Or
Yeah.
because it's just 6% of. Okay. So yeah, you can send me email. Yeah, how many significant digits are in, for example, int int 4? Just what does it mean, int 4? It means that we use 4 bits to store the number. How many numbers can we store? Yeah, 8.
I mean, like, this is both 32 density.
Almost
16
numbers.
0 to 2.
Yes, too powerful. The numbers and if it's signed, then from -7 to 8. If it's unsigned, from 0 to 15. So what does it mean float? So with ints, it's easy. We can just store in integers. What does that mean? Float, for example, 32.
All of your floats are now 32 bits. That means you have.
What does it mean, for example, when we write 2e plus 7, for example?
You have. But that's a offset. I mean, like 2 plus 7. That's a offset.
What does it mean offset? It's a new word for me. Yeah, you can.
Is it 2 times 10 to the 7th power?
Yes. And what is the name for exponent? And yeah.
you store the actual it's base 2. You store one bit is always going to be reserved for the signed bit. You have
Yeah,
a
the
bunch
first
of
bit always reserved for the sign. Okay. Okay.
powers of 2. And then you have I think it was called the mantissa that effectively stores everything as a sum of fractions of powers of 2 of fraction that stores your fraction as a sum of a bunch of powers of 2. If I'm remembering correctly, I don't know how this is exactly stored.
I think there's also the word range for the number. So we have one bit for sign. In the floats 32, we have 8 bits for the powers. And in this case, powers of 32. And that can be a huge number. And the remaining number of bits, which is 32 minus 8, or 24.
It'd be 23 bits because you're reserving, because you are reserving.
Oh, you're right.
Sign.
Yes.
So you have 20.
Because we should subtract, yes. Reserved for the significant digits. So typically it's about let's see, for float I don't remember, 32 or 16, the number of significant digits is about 9. So, for example, if you use gradient descent and you just use data points randomly, then or maybe learning rate is, for example, negative power negative 10 negative 4, then maybe it doesn't make sense to keep all 9 significant digits, and you can use float 16. If you use float 16, then your neural network, which, for example, needs storage about, let's say, 120 gigabyte, will use twice less, 60 gigabyte, for example, GPU unit. So it's good to understand a little bit which data type we want to use. So, okay. In NumPy, we had shape method to see the dimensions of array. In Torch, we also can use shape, but it also has the method size. So size will work and shape will work. Also, we have broadcasting. We created array of ones. If we add 1, it will be added to every element of the tensor. Another difference from NumPy is method view. So it's exactly the same as I mean, it does exactly the same as reshape, but it makes this in place. It makes it more efficient. So, for example, I had array of ones, and I want to reshape this vector. In this case, it will create a copy of this vector. If we use view, it will just change the first I don't know how many bits in this object. And which will just tell this variable C that we should split after 3 items. We should start a new row. So it doesn't create a new object. And if you want to make your code more efficient for neural networks, it's better to use view instead of reshape. Okay, we have one squeeze. The same operations, dot product, matrix multiplication, transposition. It's also interesting that there are in place mathematical functions. So there is, for example, x and x underscore, sign and sign underscore, and so on. It means that, I don't have example here. It means that for example, sign of x will create a new object. X dot sign underscore will change your variable in place, so it won't create a new object. Okay. And the main, the most useful for us thing that we can also differentiate our variables. So if I create a variable with this additional parameter requires graph equals true, then this variable, okay, for now, you can see will contain two actually fields. One field is data, which is the value. So I used random, so it's just random number. But also it will have gradient. And because I didn't calculate the gradient, it's none for beginning. So when we calculate the function, so b is a function of a, and it's a computational graph. PyTorch knows the derivative of sine. And so we can calculate this derivative, which will be just cosine of a. And to do this, there is method backward propagation. You remember backward derivative that we covered last week. So let's apply to our function b backward and print the gradient part of our variable a and cosine of a. They should coincide. So when we calculate the gradient of variable a, the derivative will be stored in a dot grad. And there is also method detach. Detach will remove these gradients. So for example, a dot detach, it will return so a has a gradient parameter. After detach, it will be just a number without. So for example, when you calculate loss function in your models, neural networks, the loss function will depend on all the weights and biases. And when you take the derivative, then your loss function will keep all the gradients. And if you want to keep track of your loss function, you will store your loss function on every iteration, and you don't want to store all the gradients on every iteration as well. So then we will use detach just to store the values of loss function instead of the entire history of computational graph. And here's an example. I create the random number of actually vector of size 4. Then y0 also vector with gradients. Then I use initialize y as y0 detach, calculate function z as the product of x and y, and then take the sum, and because z is a vector variable and the gradient the torch can calculate only from scalars, so we take a sum, and loss function is always scalar. And calculate derivatives, and let's print the values x, y, x gradient, and y gradient. So, four-dimensional vector for gradients for x, and we don't have gradients for y because y wasn't actually y was initialized without gradients. So, the last thing to know that you should know about automatic differentiation in Torch is not obvious. So if you calculate if we apply our function twice, for example, do I have still A and B? Yes, so you remember B was the sign of X. If I calculate B again and apply backwards, let me first print the previous values. So if I apply function again to A and calculate backward, it's let's see, sign. Should initialize A is let's say it's so sine of 0 is 0. Cosine of 0 is 1. Let's do b equals cosine. Tensor. Okay, maybe let's do sine. And derivative is cosine. So, okay, I initialized my variable a as 0, and the derivative of sine is cosine. Cosine of 0 is 1. And now I calculate again the value b and apply backward. So what can we see? The derivative of 0 cosine of sine of 0 should be 1, but we have 2 after alternating differentiation. So this is not obvious thing that torch adds up the derivatives. So I calculated the first time and the derivative was correct. It was 1. Then I calculated cosine from my variable again, calculated the derivative, and this derivative was added to this previous value of gradient. So that's why we should reset our gradient after every time we use backward methods. And to reset the gradient, we can use this method. Wait a second. Yeah, for example, here grad dot 0. So if we apply a dot grad dot 0, calculate sine and backwards, then we will get correct value of the gradient. Okay. So leaf and non-leaf variables. The gradients are stored by default only for leaf variables, not for intermediate nodes of our computational graph. But if you want to store a variable, a gradient with respect to intermediate variable, then you can force that with this method retaining gradient. So here, for example, my leaf variable is x, and variable is z, and w depends on this variable, so it's not a leaf variable. But if I ask to keep the gradient, then it will be calculated also with respect to intermediate variable. Okay, now we are going to problem solving. So we will implement gradient descent, but instead of using the manually computed gradients with, you remember, matrix notations or sums, we will just use the automatic differentiation from torch. We'll just write dot backward, and that's it. And we will get the values of gradients. So here is the data set. Some numbers between 1 and 5. And then I take a linear function with some noise with magnitude 5. So these are our points. And we want to fit a linear function. Okay, so the first step is, you remember our model is y equals wx plus b. And then we will calculate the derivatives with respect to w and b. So we should initialize these variables randomly. And we should require gradient also for this gradient for these variables. Torch dot rand twice plot equals true. And the same for B. Okay, and now the entire gradient descent will take this amount of space. So just calculate y, calculate loss, which is y minus target squared. Apply loss dot backwards and update w and b with w dot grad and b dot grad, because our gradients will be stored in these fields. Okay, so we can just copy paste this code. So this is the formula for prediction. This is the formula for loss, and then we should apply backwards. So x is a vector and y will be also a vector. Loss will be squared mean. Then we apply loss backward, and it suggests to the code. After we applied loss backward, we actually will get the gradients. So we can update W values, the data, and it provides the correct code. It will be previous value minus learning rate times I think you can use this W graph, W graph data. And the same for B. And finally, we should zero our gradients because we'll do the for loop over epochs. So let's remove this last data. So we update our values. Then we zero gradients. And this is the end of your code, actually. So, yes, the only difference from our second or the first homework is that when we wrote the gradient descent class, here we wrote the explicit expression for gradients. Now we use automatic various gradients. Yeah, and you can see that it converges. Okay, do you have any questions about this code? Yes.
So if you don't use zero, it basically adds on to the gradient each iteration.
Yes. And there's a reason for that, because um, if we want to update a batch of data points, then we calculate the gradients with respect to one point, another point, and so on. And then we can average these gradients. It will be batch gradients.
Is there a reason why any design philosophy to explain why tensor adds to the gradient in this case? I mean, adds to the
Why
gradient
the previous
every
batch?
time we call loss at afterwards.
You mean the previous bit? That's yeah. I just kind of explained this now. So if we have a batch of points, we can calculate gradient with respect to one point, second point, and so on, and then we should average these gradients. If you add the gradients, then you actually have the sum of gradients. So I think it was done just to make this batch gradient to calculate easier. Okay. So these are your basic operations in Torch. The second part of our class will be to use built-in models. Instead of manually writing this training loop, we will use built-in classes from Torch. And this is our second notebook. You don't need to submit the second notebook. So, the very important class in Torch is called data set. How we will create actually our data. They can be images, they can be audio. So let's talk about data set class. So first I will import Torch. Oh, by the way, if you want, I don't know, for some reason to use different frameworks like Torch and TensorFlow, it's a very bad idea to import both and Torch and TensorFlow. Even NumPy is not recommended to import with Torch because Torch has all the operations that you can do with NumPy. So it's kind of the unspoken agreement is to use as small packages as possible because different packages use different data types. For example, NumPy, there is another data type, float 16 and B float. 16. So the difference is that in float 16 there is 5 bits for exponent. In B float 16 it's 8 bits for exponents, so they have the same range as float 32. And NumPy doesn't have B float 16, and typically operations with neural networks are done in B float 16, which is supported by Torch and GPUs. So it's better to use the smallest possible number of packages. Then we will use data sets. So from Torch utils data import. So this code actually is on the GitHub. You can just download the ready code if you want and just follow it. Import, we will need data set and data loader. And also for visualization, we will need matplotlib. Loader with capital. And let's create data. For example, X will be array of numbers between -1 and 1. Let's see if Torch has linspace. Yeah, it has. And Y will be, let's see, what is the shape? One-dimensional, because I want to use neural networks. Remember, the input is two-dimensional, so let's do X dot view. And then the shape will be 100 by 1. Okay. Yeah, if we consider the individual point as batch, kind of one point is one batch, then the first dimension is the batch size. But then we actually will create batches with class data loader. Okay, and then we create y's as, for example, absolute values x. By the way, in Torch, you can use the functions as methods of variables. Instead of torch.apps, you can write x.apps. And let's visualize it. So if you want to, for example, for visualization, your function needs NumPy, you can cast Torch tensor data type into NumPy. But I believe the plot matplotlib works with tensors. Nice. Just because it's two-dimensional, we should do squeeze. Squeeze will remove the extra dimension. Okay, so this is our function. If we use scatter, here are our points. Okay, so let's create our custom dataset class. My dataset. So it doesn't look correct. So first we should now it's correct. So first we should add this inheritance from the parent class. And I think we don't need, so it's old way to indicate here your class name. You can just use super without any arguments in it. Then we memorize x and y. Okay. We can calculate. Okay, we don't need this length. So class dataset has three main functions. One is init, another is len. So let's write. Okay, now it's correct. So len returns the length of your data. So you can apply then, you can use len as for arrays, and len of your class will return actually the size of your, the number of data points in your class. And so we return here the size of x. That makes sense. And the third method, getItem. GetItem will return the data point from your data set by index. So the input to this function is index. And yeah, it returns X and Y with these indices. Okay. Now let's initialize our data set class. And we can use, for example, len of dataset, and it should return the number of points. We can use dataset of 1, for example. It will return X with index 1 and Y with index 1. So it will return a data point and target with index 1 and so on. The second important class for every deep learning project is data loader. So dataset creates data and it returns your data points in torch standard format. Data loader will collect your data into batches automatically. So let's create class my data loader. See if I need this. Well, actually, we can just, we even don't need to create a class. We can just call it data loader equals, and the built-in class data loader, the input will be our data set, then the batch size, and shuffle true or false. You remember for training we use true, then it will create batches using points randomly. For evaluation, we use shuffle false because the order doesn't matter for evaluation. Okay, let's create this class. And now let's look at the outputs. So for batch in data loader, okay, maybe we can print, but typically, okay, let's do this break. So in this for loop, I return one batch at a time. So because I am using break, it returns the first batch. So you can see that the first batch contains a tuple of a batch of X's and a batch of Y's of the targets. So typically, because our data set returns X's and Y's, it's maybe makes more sense to use X batch and Y batch. Batch shape and Y batch shape. Yeah, it's more clear that this class data loader will group your points in batches automatically and will shuffle your points or not. So that's it. And now we can finally create a model and train our model. So how to implement linear regression with neural network? So you remember that neural network takes inputs. In our case, the input is one-dimensional actually. So in our case, input will be just x. Then it applies a matrix for linear regression. The matrix will be one by one because it just double your weight. So we will get the hidden vector where h will be just wx plus b. Of course, it's a very simple model, but we can use neural network to implement linear regression. We can use more complex model to implement simple model. So, and that's it. And this will be actually our output. So it means that we should, let's see. Am I using? Yeah, I'm using the neural network. So this is kind of neural network, but without any activation functions. So the class that contains linear model, linear layers, activations is called Torch NN, Torch neural networks. So let's import this class. And this module contains class model. So we will create our model class. That will depend on this nn.module. Okay. And actually, the suggestion was correct. And we create linear layer with input shape 1 and output shape 1. So linear layer, you can indicate bias equals false. By default, bias equals true. So it will be exactly this formula, wx plus g. If you use bias equals false, it will be just wx. And in this class, model class, we should write only one function forwards. Because backwards will calculate gradients automatically. We don't need backwards. So in forwards, we apply this linear layer to our FC stands for fully connected. Sometimes linear layers are also called fully connected because you remember all these elements from input are connected with all limits with hidden. Okay, that's it. Um, well, yeah, it's a very dummy model. So initialize our model. And finally, we will write the training loop. Again, all these steps you will repeat for any deep learning project, any deep learning projects. Data set, data loader, initialize model. Now we will also initialize optimizer and training loop. It will be always identical. The difference will be in your data loader because you will use different data, and in model, you will use different models. So we will need to import a loss function. Let's see, maybe I can just use, or you can import function, or I believe you can just use an n.mse loss. Let's see. Criterion, and yeah, we can just use an n.mse loss. Also, we will need optimizer. Next time we will talk about how this optimizer works, but the default optimizer for neural networks is called ADAM, adaptive momentum, which is modification of gradient descent. There's also SGD, but you saw last time that SGD is not very efficient. You need to do a lot of iterations with vanilla SGD. So optimizer. In optimizer, you can indicate learning rate. By default, it's 1,000 negative 3. This is default parameter. And you should, in optimizer, pass the parameters of the model. So when we created our model, it has parameters. Mm. Let's see. So yeah, this is how our model looks like. Linear layer, input features, output features. How to see the weights, the values of weights. Maybe it's dot layers. Model dot let's see. Named parameters. Mhm. Let's see. Okay, so looks like parameters is iterator, and we can just iterate and print parameters or the values themselves. So these are current values of our W and B. And they, you can see, requires grad equal true. Okay, so we pass these parameters into our optimizer because optimizer will update these parameters. And finally, we can write the training loop. Let's keep track of our loss, history of loss for epoch I hope this code is familiar. X batch, Y batch from data loader. Let us read XY. Then we apply model to X, and this will be our prediction. And finally, we calculate the loss function between prediction and true values. And it's important that in scikit-learn, when you calculate metrics, the first parameter is true value, and the second is prediction. Or maybe it's opposite. Let's double check. Torch MSE loss. Yes, in Torch, the first is prediction and the second is start. So it's a good practice to double check the order of arguments in your functions, because it will calculate the gradients with respect to inputs, not with respect to the targets. Okay, and what we're doing next? Do you have a question or you just switch? Huh? Okay, so we calculate gradients. So we apply loss dot backward. Loss dot backward. What it does, it calculates the gradients of LSE loss with respect to leaf variables, and the leaf variables will be X, Y, W, and B, but only W and B, they has this required graphs equals true. So it won't calculate the gradients with respect to X and Y. If you want, you need to indicate gradient required graphs equals true. And finally, we should perform the gradient descent step, update our weights. And this is done like under the hood by command optimizer step. Optimizer step will actually update the parameters that we pass to our optimizer to subtracting gradient times this learning rate. And then we should zero gradients, so this is important. Optimizer zero that. And here we store the values. Loss.item will actually detach the item, so it will store only the value of loss function. And let's plot the loss function. Not a good name. Looks like histogram. Okay, so here's we can see that the model converged, and so this is MSE loss, and we can actually plot the prediction. So this is the last important thing. When we want to apply our model for example, predictions, we don't need gradients anymore. And there is so there are two things that we should do. We should use model dot eval. It's not important for now. For training, we should write model dot train. If we so for this week it's not important, but when we will talk about Bayes normalization or dropout, then it will be important because Bayes norm and dropout we apply during training only, and we don't want to apply them during evaluation. So for now, it's not important. So I can actually comment this. But which is important for now? Yeah, okay, I understand. We can use this what's called with torch no ground. That means that all the calculations are inside this statement will be performed without gradients. And yeah. So this is how we calculate the prediction. And let's plot this prediction. See dot plot. Okay, and prediction doesn't look great. So let's a little bit modify our model and add one hidden layer. So let's create activation function. For now, we know just sigmoid. It suggests ReLU, but for now, let's use just sigmoid. And one more linear layer. So let's use hidden size. So we can use in our init the hidden size, for example, uh, hidden size equals, let's do by default 3. Linear will go from 1 to hidden size. And then the second fully connected from hidden size to 1. So in our forward, we will first apply fully connected activation and then fully connected. So we just added extra linear layer. By the way, why it's a good idea to use the same variable here? Just again, it will save your memory. If you will write x equals then a equals then output equals, it will create more variables. And okay, now it looks better, the approximation. Maybe we should train for more epochs. And we will get a better, yeah. So you can see the approximation now is better. Okay, that's it for today. Now you're specialists in deep learning. You can build arbitrary model from just building blocks, just add more layers, add more activation, and play with hidden side parameters and so on. And this is what people are doing in practice. Okay, don't forget to submit your notebooks. The last problem solving